This is Dan Olds, and this webcast is going to be all about the MILC application that's going to be featured in the upcoming ISC'13 Student Cluster Competition. Today on the phone I have a couple of guys that are genuine and perhaps even certified experts in MILC. I have Steve Gottlieb and I have Carlton Datar. Hey guys, say hi.
Hi.
Hello.
That was them saying hello. So Steve, tell us a little bit about yourself.
I am a professor at Indiana University. I've been here since 1985. I've been working in lattice gauge theory since the early 1980s. And Carlton and I are both founding members of MILC. In addition to lattice QCD, high energy theory, I enjoy bicycling.
Excellent. Carlton, what about you?
I'm professor of physics at the University of Utah, and I've been here since 1978. Have enjoyed being a member of the MILC collaboration now for at least 2 decades. We have done a lot of calculations on most of the supercomputers in the country. Probably have accounts on every one of them almost. And so we've had a lot of experience in high-performance computing. We've enjoyed very much producing interesting physics with this code. Aside from doing physics, I'm also an avid hiker and love exploring the backcountry in Utah.
So, jumping right into this, can one or both of you tell us, what is MILC? What's it do?
Well, MILC is an acronym that stands for MIMD, meaning multiple instruction, multiple data, lattice computations. The MILC collaboration is a group of high-energy physicists who are studying the strong interactions. And Steve can chime in if I miss anything here. We're essentially solving for the interactions of quarks and gluons and using this technique in order to investigate the properties of protons, neutrons, and mesons, various hadrons, and also to study processes that will help in searching for new discoveries, helping to interpret experiments at the LHC and other accelerators, and so helping to push the frontiers of physics forward with our calculations.
Steve, is that about right?
Yes. Let me add that the MILC collaboration is over 20 years old, and I think we've published probably over 200 papers together. Some people refer to the code as the MILC code. We do. And so you have to be careful about whether someone's talking about the collaboration or the code. And often people just say, oh, are you running MILC? And that's not the name of any of the executables, which
Gotcha.
can be a little confusing.
That's more the project name and the collaboration name.
Yes, and the code is open source. It's served out of the University of Utah, and Carlton is our code master. And people use it and adapt it. And sometimes they even send us code back to improve the code. We've also been interacting with US QCD, and there are parts of the code that are enhanced by the scientific SciDAC program, Scientific Discovery Through Advanced Computation, and we've been supported by that for a number of years, as well as the Department of Energy and the National Science Foundation.
Great. Are either one of you going to be at ISC this year?
Not I.
No.
Okay. Well, we'll be sure and post plenty of pictures and videos, and you can see the students puzzling over the code and making it hopefully sing. So let's jump into that. Put yourselves in the place of these students that are reasonably new to HPC in a lot of cases. First time they're in a big competition, and this is one of 3 or 4 applications that they need to optimize and be able to run screamingly fast on some real hardware, probably 200 cores or so, maybe with accelerators like Intel Phi or NVIDIA GPUs, maybe with them, maybe without them. So what would you guys do with MILC, or with MILC? See, I fell into calling it MILC just now.
That's what we call it. You should call it MILC.
Then I will. So what would you guys do with MILC?
Well, I think the first thing I would do is get a hold of a copy of the code. And there's a website for that.
Which I'm going to put in the video here.
So you're going to provide that for the audience.
Yes.
Then you need to choose which version of the code you want to work with. And of course, this is going to depend partly on how the competition is framed. I think that's something that the organizers are still deciding. But what's available from that site is, first of all, the latest stable release, which is about over a year old now. And then there's an alpha release which supports a lot of the new features in some of the accelerators. And so that one ought to be able to run the benchmark that the competition requires, but it might not run some of the other things because it hasn't been thoroughly vetted yet. That's why it's an alpha release.
So students should have been up grabbing the code and testing it out and getting a feel for it already.
Yes, and we've gotten some nice responses from them, many of them.
Oh, good.
Anxious responses in some cases.
Help! What's going on with this? That sort of thing?
Well, how about, oh, this doesn't compile?
Yes, really it's that sort of thing. So, as I said, I don't know what benchmark the organizers are going to choose. If they choose one of the older ones, then the code might not support it because it's not something that is in our current production stream. If they choose one of the newer ones, then you probably need the alpha version in order to run that one. The next step would be to read about how you unpack the code, and there's a tutorial on that code webpage that describes it.
And I'm going to have those slides from that running underneath our audio at this point in the conversation, and make sure I have links there because that was very helpful.
Good. So would you like me to start going through a couple of pages of that? Or
Well,
how would you like?
Yeah, it was fairly self-explanatory on how to unpack and get the code up.
Well, maybe you want just a kind of an overview of the things to watch for.
I think so, yeah, sort of tips and tricks and again, what would you two do as seasoned veterans and professionals in this in order to blow out the competition?
Well, Carlton,
Or at least not embarrass yourself.
do we know whether they're going to demand single or double precision?
That we don't know yet.
I don't think we know, no.
So the first thing I would do is make sure that if single precision is allowed, I was using it.
Mm-hmm.
Precision is one of the variables set near the top of the make file.
Okay. And there are versions of this code that will work with accelerators, right?
Yes, so there are a number of options for building this code. The code can be built as straight C code, which is sort of the original generic version, but it can also be built against the SIDAC optimized libraries, and that requires installing a package and then making the necessary selections in the make file. It can also be built to run on GPUs. That GPU support comes through a package called QUDA, Q-U-D-A, and so that package needs to be installed along with the MILC interface that goes with it. And then the appropriate options in the make file have to be selected. Then another option is to compile it with some OpenMP directives. This is something that is very rudimentary in the code at the moment, but we at least have some macros that will convert loops over a long list of data into an OpenMP directive loop. So it can be broken up into threads. And that's the support that we've been using at the moment for running on the Xeon Phi. But as I said, it's very rudimentary. That's quite to us, brand new. We've only had access to those in the last few months.
Yeah.
And so not all of the modules in the code have that support yet, so there would probably have to be some hand code changes in order to support threading in the modules that are needed.
And that's for Phi specifically?
For the Phi specifically. So that somebody would actually have to get into the code and probably make some changes if they wanted to get good performance out of the Phi.
That's not just for Phi, by the way. It's really a question of having a hybrid of OpenMP parallelism with MPI parallelism. So one could potentially experiment with having multiple OpenMP threads and fewer MPI tasks.
Yeah, thank you for that correction, Steve. That's quite right. But again,
and in fact, let me mention that if they're doing something on the GPU and they're spending significant amount of time outside of the parts of the code that are already in CUDA, then they might consider adding some OpenMP or using the OpenMP directives in other parts of the code that aren't running on the GPU. Because when you run on the GPU, there's only one host core used per GPU, which often leaves many host cores idle.
Yeah, that's a very good point. I was just actually thinking that reminded me of something else I saw at GTC, some presentations on using for very compute-intensive code where a lot of it is running on the GPU using RDMA for inter-GPU communications. Is that useful at all with MILC?
Well, that would have to be supported through CUDA, and I think that is being done now.
Okay.
Is this something different from DirectX?
I believe it is.
Oh, well, then I wouldn't know. I thought that was the same.
Well, and again, I've got the technical knowledge of a gray squirrel, so I could be wrong. But I believe it's separate. It seems like it's a new feature that came in through development by Mellanox and NVIDIA. So, well, that's an open question. That's something the students should investigate for sure. So we kind of get down to performance characteristics of MILC. I'm assuming this thing is quite compute intensive, but is it also memory intensive?
It's mostly memory bandwidth limited.
Oh, okay.
Which is typical of a lot of high-performance applications.
I had someone tell me at a conference in the last couple of months that every problem in HPC, if you optimize it correctly, should be memory bandwidth bound ultimately.
Well, that's possible.
Yeah.
Well, if you're doing ordinary arithmetic, you have to bring in 3 operands to do one flop, and in single precision at 4 bytes per operand, that's 12 bytes. Well, 8 bytes of input per flop and 4 bytes of output in single precision. Our code is not that intensive, fortunately, but we still use 1.45 bytes per flop, if I remember correctly. But generally, the bandwidth of modern CPUs is much lower than that. And we're not memory intensive in terms of usually having a large footprint needing a lot of memory. Generally, we like to try and spread the code out over as many cores as possible because that's how you get the large peak performance. If you can make each core go at a quite reasonable speed and spread it out, you get high performance.
So as many cores as possible, but it doesn't necessarily need the entire footprint of system memory.
Right. And typically, we do benchmarks by doing weak scaling. As far as I know, this competition is a competition on a particular size input file. And that means you spread it out until the performance either is inefficient or the performance actually can decrease. This is what happens with strong scaling. And, usually there's some spot where the performance is high enough and you don't want to go further even though the performance will go up because you're using up more of your allocation and getting less total work done. At least that's the way we work. It depends on the rules of the competition. If the competition is to get the highest performance and you have an unlimited amount of hardware available, then you'd run it possibly in an inefficient region.
Just to max out performance.
Right.
Yeah, it depends on how they calculate performance. When we run at high-performance computing centers, of course, they're interested in the parking limit and how long you spend on each one of the cores, and then to optimize, you try to minimize the number of nodes that are required because you have less communication going on.
Mm-hmm.
But if the competition is just to get the job done fast and it doesn't matter how many cores you use, then what Steve says is right.
I think it's going to be more towards the latter. The major competitions vary a little bit. The one at SC typically gives them 4 or 5 applications that they have to run over a 3-day period. So they have to sort of divvy up the machine and figure out, based on the data sets for each application, the tasks they have to do, how to allocate the machine from there. The ISC competition, which is the one we're talking about, typically they run these applications in isolation. So they'll have half a day, for instance, to do MILC, and maybe half a day for GrowMax, that sort of thing. So it's going to be more of a sprint.
So what is the goal during that half day?
I believe it's going to be to get the highest performance, or to run through the largest set of data. But I'm not
positive. If it's
positive.
the largest set of data, one possible strategy is to run two jobs, not one job, and you might be able to run each one at a higher efficiency and get more total output. We often do that at the supercomputer centers. So ideally, we'd run one long stream when we're creating gauge configurations, and often we split it into two or maybe a few streams, and this can help get more work done.
Would that pay off regardless of the size of the system? These are probably going to be 8 nodes at the high end, I would think.
I wouldn't make any blanket statement. I really need to see what the rules are.
Sure.
And whether that's even feasible within the rules.
It is, I believe. It should be. But we'll see. But it's something for the students to think about. And is there? I'm sure there's a point where you get diminishing returns from starting up new instances of it.
Yes, in our case, it's physics returns that may be not as good. We spend too much time warming up, and ideally, we would like to have one very long stochastic simulation. So you sample very long evolution times rather than several shorter evolution times.
And are there any sort of traps when trying to optimize MILC on systems? Anything, common mistakes that you can help them steer around?
There must be repressed memories of that.
That's not a technical term, repressed memory? I'm trying to go to Wikipedia to see if that's some sort of a memory state that I'm not aware of.
You wouldn't remember.
Good one.
Can you think of some common pitfalls, Carlton?
Well, I guess that sometimes in the past we've had trouble with extra aggressive compiler optimizations, just choosing the standard compiler flags. I mean, certainly you can, in some cases, do better if you choose the right compiler for the code. So I think on the Intel machines, we've been trying to use the Intel compilers because they're a lot more familiar with the latest architectural tricks.
That's good to know.
They may also have a choice of different versions of MPI, I imagine.
Sure.
And that can make some difference. So they should test different versions.
Any version you want to tout as being particularly good?
I think
I have trouble remembering.
Okay.
And it may depend. Pardon?
I think it depends on the center, but we've typically used MPitch.
And you've seen there can be significant performance differences.
There can be small performance differences depending on which version you choose.
Well, these kids are all laboring under the same constraint, which is going to be the amount of electricity they can use. And so even a small difference can make the difference.
Are they going to be graded by power consumption also?
Not as such. They are limited to using 26 amps. That's if you were measuring US, so it's 13 amps there. It's really about 3,000 watts. And if they go over, I believe this year there's a penalty if they go over it. So that's what's capping them on the hardware side. But they can do pretty much anything they want to do hardware-wise and software-wise as long as they're within that constraint.
Well, we don't have a lot of experience with power consumption with our code and trying to economize, so can't offer a whole lot of advice there. I presume that limiting communications would help.
Mm-hmm.
That running with larger subsample sizes. So there is a way of controlling how many cores you put a given problem on. If you start to have to use the switches and going off from one board to another, I suppose that would increase power consumption.
Yeah, it probably would. I would think that what might be more important is to make sure that if they're running something that's pretty power hungry like GPUs, that they're getting the full computational value out of them, or PHYs for that matter.
You might be interested to know that I was at a meeting at the Argonne Leadership Computing Facility, and I think it was Pete Beckman who said, when MILC comes on the machine, the fans always run at full speed.
Okay, so it's generating some BTUs then at least.
The code was designed for performance, not for energy consumption.
Well, good. We're going to put that to the test, at least the students will. Well, any final advice for the students on this, on using MILC and learning about it and, again, making it scream in the competition?
If you make it go faster, let us know what you did.
Agreed.
Okay, so you guys are looking for performance tips yourself.
Yes, indeed.
Excellent. Well, this has been great. I really appreciate you two taking the time, and you'll be able to see what's going on with the competition on this on the www.studentclustercomp.com site, and I'll also be posting in the register. And thank you very much for taking time right before a big holiday weekend. We appreciate it.
I enjoyed it.
You're welcome, Dan.
Great. We'll talk to you soon.
Bye.
Bye-bye.
I know.